Okay, welcome. This is a question-by-question explanation of midterm review topics that you'll face in roughly a week's time. This is probably going to be a part 2 video because I think I'm going to exceed 15 minutes well before I finish it. So it'll be clear on the videos which one is part 2, which one is part 1. We'll just start from the beginning. Notice A and B are all about what we call dimensional analysis, which is unit conversion. Now, what you guys have to remember is, let me pause for a sec. You need to remember what the different quantities, what the different unit relations are. If you recall, centi and deci, centi is always equal to 10 to the 2. There are 10 to the 2 centimeters, or I should say in this case centiliters, in 1 liter. That's the base unit. And there are just 10, or 10 to the 1 deciliters in 1 liter. So that stands to reason that there are 10 to the 2 centiliters in 10 to the 1 deciliters. That's going to be the basis of my conversion factor. So I'm going to write down what I'm given, centiliters, and my destination is finding out how many deciliters we have. Now remember, whatever going to goes on top. So I'm going to go to deciliters, that goes on top. I have the relative value of deciliters, the value relative to the same quantity of centiliters. I've stated this already. I've said that there are 10 to the 1 centiliters in 10 to, sorry, let me try that again. There are 10 to the 2 centiliters in 10 to the 1 deciliters. So when I do this, I can do this one of two ways. I could say 10 to the 1 divided by 10 to the 2 is equal to 0.1. And then 0.1 times 50 is just 5 deciliters. That'd be one way of approaching the problem. In 1b, in this case, we are converting from kilograms to micrograms. If you recall, there are 10 to the negative 3 kilograms in 1 gram. And of course, 1 gram is equal to 1,000,000, or 10 to the 6 micrograms, which makes these two equivalent units. Let's set up our problem. We have 6.25 times 10 to the negative 9 kilograms. And I want to find out how many micrograms that is equal to. I make a conversion factor. Remember, it's not enough to move the decimal. I think that's actually rather dangerous to do here. You have to show your work in the form of a unit conversion, what we also call dimensional analysis. Whatever I'm going to goes on top, so I'm going to put that 10 to the 6 up top, micrograms, and downstairs I'm going to put 10 to the negative 3 kilograms. Now, for the sake, if you want to put this into your calculator, remember you can do the following. It would look like this. How do I render this in that EE notation? Well, I do the following. I say 6.25 second-hand comma, that's going to produce an E on the display, minus 9. That and that are equivalent to each other. Times, open parentheses, 1 times 10 to the 6 is 1e6, divided by 1e negative 3. When I do that, well, 6 minus a minus 3 is 9. So this is, by itself, 10 to the 9. Oh, take a look. 10 to the 9 times 10 to the negative 9, they cancel, leaving you with 6.25. Yay! Number 2. We have 3 questions here, but probably on your actual test, you'll just maybe have 1 or 2 of them. We're asking B and C. There's a point behind that, and it'll be clear to you why we've asked so many questions in the practice. Write the expanded configuration. The ground said, let me say what you don't do. Don't do this. You will get no credit if you look up on your reference table and that you see that argon's 288. That's a condensed configuration. We don't want that here. We want the expanded configuration. Well, how do I do this? Well, if you remember, I have my fun little way of remembering the order in which the energy levels get built up. And I say the following. Give me an S. Give me an SP. Give me an SPD. Give me an SPDF. Go Cyclones. How does this help? Well, recall that this is the first energy level. These are in the second energy level. These are in the third energy level. These are in the fourth energy level. Of course, there are more than 4 energy levels, but generally speaking, we don't get beyond something called the 5s. That's going to be the end of the line for us. We always fill electron sublevels in a diagonal order. So you first start off by placing electrons in the 1s. Then, once that's filled, this can have a total of 2 electrons. Next, I come back down here, and I go this way. Now I fill up the 2s. That can hold 2 electrons maximum. Now, if I have more electrons, then I come back down here, and I go up through the 2p. The 2p can hold 6. If I have more electrons, I keep going. The 3s, and that can hold a total of 2. If I have more electrons, come back down here, and I come to the 3p, which can hold 6 electrons max. Oh, notice, I don't go directly to the 3d. First, I have to go to the 4s. Very important. I can put 2 electrons there. If I have more to place, then I come back down here, and I go to the 3d, which can hold a whopping 10. And if I have more electrons, then I go to the 4p, which can hold 6. And as I say, you may get, but probably not, to the end of the line, for which you would put a remaining 1 or 2 electrons there. Okay. Well, let's talk about argon. Argon has a total of 18 electrons. Why 18? Well, if I look up the atomic number, I see that it is 18. I have 18 electrons. So I start like this. I start off here with the 1s. I put the first 2 electrons in the 1s. So that 18 electrons becomes 16. Next, I'm going to use a different color here. I'll use black. So I just I filled up the 1s. Now I'm going to go to the 2s. And I'm going to place my 2 electrons there. That fills that sublevel up. That leaves me with 14 electrons. Now I come back down, and now I can go to my 2p. 2p can hold a total of 6 electrons. Use my same nice little color scheme. So 14 minus 6 is 8. Okay. Now I continue past, and I go up to the 3s. And the 3s, notice, can hold a total of 2 electrons. 3s and 2. So now that leaves me with 6 electrons to place. Where do I go now? Well, I then follow my little trail down here, and I go to the 3p. Oh, notice, guys, 6 electrons, and I happen to have 6 left. It was 8 minus 2, giving me 6. And now, 3p6. Ding, 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 ding. So that is the expanded electron configuration for argon. 2b, chromium. Chromium has an atomic number of 24, meaning that unlike argon, which only had 18 electrons, I need to place 24 electrons in chromium. But the nice thing is, I already know what the first 18 look like from my example. So I can just bring this down as being the foundation for chromium. So chromium also, the first 18 of chromium's electrons are arranged in the same exact way. Same foundation, as I said. Okay. So remember, I had gone here, gone there, and I had just finished here with the 3p6. Now, I've placed 18 electrons. That leaves me with 6 electrons left to place. Well, notice 2 of them are going to go in the 4s. So I'm going to put a 4s with a 2, and 6 minus 2 is 4. Now I have to come down here, and I have to go to the 3d, and I can have 10 here, but I only have 4 to place So it becomes 3d4. Now, here's the reason why we're asking these two. These are both exceptions. It turns out that this is a little bit different than what it actually is. Why? It turns out that this atom's electron configuration is a bit more stable if I have one electron here and 5 electrons here. So in other words, these are so close in energy, one of these electrons makes a transition from the s to the 3d. Now why is that? It turns out this is half filled, and that means it's more stable. So when you write your final answer, it needs to look like this. You'll get partial credit if you do this, but remember, full credit requires that you write this somewhat modified configuration. Okay. So what I did is I reset the configuration to what it looks like without any modification. I do that because this is going to be the foundation for copper. Copper has 5 more electrons. So what we're going to do is we're just going to add 5 more electrons to this. So remember in this case, when we got to here, we had 4 electrons left to place, and we put them there. But here, if I went with copper, I'd have 9 electrons to place. So instead of putting a 4 here, I would put a 9 here. So this is what initially copper's configuration comes out to be. But we also have to make a slight modification here. Remember, you only get partial credit for writing this for copper. Why? It turns out that concerning the same 2 outer sublevels, that copper is more stable if one of these electrons makes a move and goes to the 3d. So I wind up with a 4s1 and here a 3d10. Why is this more stable? Well, now this is a full outer d sublevel. Full outer sublevels give an atom a bit more stability. So your final answer for copper is this. Again, if you do this, like so, you'll get partial credit. For full credit, however, you have to reflect that copper is an exception, just as chromium was an exception. Number 3, I think I have just enough time to do this one. This is the famous triple point diagram. Recall you have these 3 lines here, and you have this point which connects the 3 lines. This is called, it's a little out of sight here, this is called the triple point. This is the point at which all 3 phases are in equilibrium. And so what I would recommend is when you see the phase diagram, before you do anything else, label the regions. Remember, this region here, which is C, that's all solid. Particles here at this temperature, and I should say at these combinations of pressures and temperatures, the substance is in the solid form. Here it's sandwiched in a liquid form, and here we have the gas form. So if they ask for what is the triple point temperature, well, you just read here, that is negative 15 degrees Celsius. If they also ask for the pressure, that appears to be 6 atmospheres. Now be careful, if you left off the negative 15, you don't get credit for that. But it's a really very simple question. Part B, it says, what phase change occurs from C to B? Well, this is the benefit of writing the symbols, solid to liquid. We call that, of course, melting. I think I have just enough time. What is part C? What is the name of the phase change that occurs when pressure is decreased from 30 down to 1 at negative 100? So that means here, guys, here we're going from a solid down over to a gas. What do we call that? That is sublimation. I've just finished, and I'm thinking maybe this might even be a 3-part video, we'll see. So for question number 4, stick around, go to part 2. See you on YouTube.